apex, I guess, of the path. So we'll pick the heaviest isotope and run that one in the same parameters, and there's what you see. I think that's consistent with what you were predicting, Ms. Mitchell, if I heard you correctly. And maybe, I'm not sure exactly about the water analogy. Didn't follow that exactly, but the outcome of your analogy, I dig, and we see it here. Everybody good? And so you can, let's see, it will not let you vary any of the instrument parameters once you get those set without deleting the previous traces, the previous runs. Right? I don't think it will. Will it? Oh, yes, it will. Never mind then. So let's do this. Just to give you an example. Now we'll go with the same isotope, or the same analyte, the heaviest of the ones listed here, plutonium-24, and we'll make that magnetic field as weak as we're able to do. You get that sort of trajectory. Right? And we crank it up to the strongest. Whoops, it did. It got rid of my trace, didn't it? Oh, no. So if you change a parameter, you're not going to get to. You can only overlay traces when the parameters are set the same, looks like. There's that one. Yep, sure enough, it'll erase your trace and change the parameter. So it's a nifty little simulator. I'll have some questions related to it. I'll send the email no later than probably midday Sunday when I hit the road for Virginia. Get you guys started on that. All righty. Is that where I was? Goodness gracious. Oh, I guess I have to exit the full screen mode. Pardon me 1 second, guys. We'll get her up and running again. Oh no, how long will this take? How many clicks? About a few dozen. Takes that escape bit, doesn't it? Here's what we'll do. Where were we? You can see we're pretty close to being done. Just a few more mass analyzers. Here we go. As a matter of fact, if y'all don't mind the slightly smaller scale, I'm going to stick with this because the actual slideshow mode is having a little difficulty today. So, in terms of mass analyzers, arguably the concept underlying this mass analyzer, its function, is simpler than the one before. I know that earlier I said that maybe the magnetic field or the magnetic sector, the B sector analyzers are the simplest to conceive. Well, I take that back. I think it might be the time of flight analyzers, because there are several unique traits here that lead to this conceptual simplicity, I think. It's a so-called, check the very first bullet there, guys, field-free. Now, you'll notice a common theme for all mass analyzers except one, and this is the one. The common theme for all the other mass analyzers is that the charged analyte species, right, they are forced to interact with magnetic or electric fields, sometimes both, but magnetic and or electric field interactions give you the mass discriminating ability. As we saw for the magnetic sector, it's based on a spatial separation of those ions of different mass to charge ratio by the Lorentzian interaction with the magnetic field. And we'll see a couple other examples where electric fields are involved. In this case, no field. It's a field-free region, time of flight. Basically, think about it this way. Those ions are ejected from the source with different velocities based on their mass to charge ratios. Well, just let them proceed through a field-free region until they strike the detector. You need a pretty fast response detector, but basically it's like a race. Right? The ions are all generated essentially at the same time with the same kinetic energy, but hence different velocities based on their masses. And then the lighter molecules, smaller mass to charge ratio, they'll come out of that ion source with a higher velocity, and they'll reach the detector prior or before the heavier ones do. Are y'all seeing this in your minds? Maybe we could.
So they vary in ways that they detect mass, these two instruments.
Haven't got to the detection yet. I mean, the detectors are required, obviously. That's pretty much the end of the line in terms of instrument components. But we began with a discussion of how you generate the ions, the ion sources. Talked about a few possibilities there. And now we're talking about how to actually sort or analyze the ions generated, how to discriminate ions of different mass. You can either force them through a magnetic field, right, and then exploit the Lorentzian force, right, the different curvatures of their paths to spatially separate them and detect them that way. Or you can follow this approach right here. Let's see, is it gonna let me do this? Oh, it's gonna let me do it, great. So here's a nifty little animation. Let's see, it's not getting there to click. Hang on one second. Where's my pause? It's right there. Boom. So you generate ions, 3 different ions, and sorry I didn't pause it earlier. Let's see if I can back it up just a little bit. Yeah, here we go. Nice. Are you going to stay paused for me? Yeah, great. So you generate ions here. This depicts 3 different ions, 3 different masses, right? Red, yellow, and green spheres. They're all generated in the ion source, and they enter, and they are ejected with a roughly equal kinetic energy and hence different velocities. And they proceed through this field-free region, a lot of times called a drift tube, but a lot of times called a drift tube for that reason. They're not really drifting in the strict sense of the term, they're undergoing migration, right? They're traveling, actually no, they're not, I take that back. That would be a field. They are drifting in the field-free region, right? They have been accelerated towards the detector. So as this proceeds, obviously, the green spheres are traveling faster than the yellow spheres, which are traveling faster than the red spheres. So what's, of the 3, which is the most massive, or which has the highest mass charge ratio? The red ones, the intermediate, the yellow, and then the lighter, or the lightest of the 3 are the green ones. And so you see what's happening over here when they strike the detector. What you'll see on the far right of the simulation is detector signal as a function of time. Like boom, first you'll see your peak there for the lightest of the 3, the green spheres. And there's a peak for the moderately massive green spheres, and then finally the most massive red ones. So you get a plot of detector intensity versus time. The time can be related to the mass to charge ratio because of the phenomenon we just discussed. See, it's a square root dependence. So that x-axis of the raw signal can be converted easily to a mass to charge ratio. You get a mass spectrum that way, a plot of intensity, which is the quantitative parameter. It reflects the relative number of ions of that particular mass to charge ratio, versus on the x, the mass to charge ratio. That's the qualitative parameter, indicative of the identity of the substance. Everybody good on that? Have you picked up on the fact that I've said several times that the ions are ejected from the source with roughly equivalent kinetic energies? I mean, I probably said the same kinetic energy several times, but a few times I probably said, oh, roughly equivalent. It all depends on the specific point within the ion source where the ions are formed, the direction they're traveling when they're formed, right? Inhomogeneities in the electric field will cause the ions, even ions of identical mass to charge ratio, they might be ejected with slightly different, with a spread, that's the word, with a spread of kinetic energies, because they are created at different points within that field in the ion source, and that might be slightly different field strengths, and so they get accelerated with slightly different energies. And hopefully, careful engineering and construction will avoid any kind of serious problems with that. Did I open this already? I say open hyperlink. So here's a similar simulation, which is kind of tough to say. Where are we going to go? What do y'all think? Is it there already? Is it the same one? Yeah, it's not the same one. Great. What's the difference, you say? Well, we'll look more closely now. As opposed to the ions emerging from the source with exactly the same kinetic energies, hence exactly the same velocities for a given mass, right? Notice that that red sphere is traveling a little faster than that one, and that yellow sphere a little faster than that one, and that green sphere a little faster than that one. So there's a spread of kinetic energies against velocities even for the ions of the same mass to charge ratio. And so you'll see that they don't strike the detector. Ions of the same mass to charge ratio don't strike the detector at exactly the same time. And they arrive slightly different times. And so you don't get those theoretical, infinitely sharp features. Instead, there's a finite width to the features, as you can see in the mass spectrum that's plotted out over the right there. You get actual, peaks of finite width as opposed to lines of infinitely narrow width. Everybody good? Great. You can help yourself out a little bit. I mean, that's not a big deal if you have large differences in mass to charge ratio for the different components of your sample. But imagine that the mass to charge ratios, the masses for a couple of different ions, are pretty closely spaced. They might be so closely spaced that the width of each individual peak causes overlap, interference, difficulty in resolving the two from one of those two signals from one another. And so there are some approaches to get around that. You can construct your ion source as carefully as possible. Please ignore some of the details of this ion source. It's actually taken from a different literature resource. You see laser down here, and that's not involved in any kind of typical electron ionization. It's a different kind of ionization scheme, but the mass analyzer part is what I want you guys to check out. That's right here, after the ion source. Just ignore the ion source. Ions are generated. They're sent into this time-of-flight mass analyzer. There's, again, the field-free region, the drift tube, as it's called. But the path is just not a straight shot to the detector. The ions travel through this drift region, field-free tube, the drift tube, the field-free region, and then they encounter the electronic analog of a mirror, right? The reflectron, as most people call it, it's an electrostatic mirror, basically, where the ions are redirected towards the detector. This does a couple things, actually. It permits you to introduce a longer path of travel for the ions, which will help with resolution, right, improve resolution. And speaking of resolution, this reflectron, the nature of the electrostatic reflection process, will help to narrow down the differences. It will help to sort of, I can't think of a word right now. I'm feeling a little pressed for time. It will help to reduce the differences in kinetic energies for ions of the same mass to charge ratio. Here, I think, is a little illustration, a little simulation that might help you see this process a little better than I am helping you see it with my words. Okay, so here come a couple of ions of identical mass to charge ratio. And you can see, we're being realistic, they're actually traveling at slightly different velocities because the ion source in that process is not perfect. And so, as they travel through the drift-free tube, notice that the distance between them is getting greater and greater. Right before they encounter this reflectron, check out the difference in distance. It's more than a flower's hand length different, okay? And now watch slowly. Ooh, how do you slow this bad boy down? I'll just pause my way through it. But the ion that was traveling a little faster actually penetrates this electrostatic well a little further. So it has to travel a little bit further before the electrostatic repulsion is enough to reverse its direction. As opposed to, check it out, for the one traveling slower, it didn't have, it was lesser momentum, it didn't penetrate that electrostatic well nearly as far before it got reversed. Did you guys notice that? Mm-hmm. And so the one that was traveling faster had to penetrate further before it got slowed and redirected compared to the other. Oh. And so that ends up, now look how much closer they are to one another. They were originally more than a flower's hand apart, and now that's just a couple flower finger widths, if you know what I'm saying. And the detector here, by the way, is on either side of this entrance slit from the ion source. So notice that when they strike the detector, there goes that little peak. It's drawn as an infinitely narrow peak, but it'll be a reduced width feature. Right? Reducing the spread of velocities, hence the width of that mass spectral feature when you use that reflectron. Everybody good? Awesome.